So we're going to shift gears a little bit from looking at standing waves on strings and pipes and whatnot to looking at the energy in waves and how that travels and how that affects how we hear different sounds. One of the first things we mentioned when we looked at waves is that they are carrying energy. That's what's being transported. And we're going to define a new quantity called the intensity of a wave. And the intensity is the rate of energy transfer per unit area. Nice fun definition there, right? Well, energy transfer, rate of energy transfer, is another term for power. So intensity is simply the power divided by the area over which that power is distributed. And we can break up power into energy per time divided by area. If you want to write it more shortly, these are the abbreviations. We go ahead and just use a plain old I for intensity. The units, since it's going to be power over area, and power is measured in watts, area is square meters, so we've got watts per square meter. There isn't some other redefined unit that equals a watt per square meter. Just to get kind of an intuitive feel for what we're talking about with intensity, one way to look, or one example of this, is the intensity of the sun's rays. And in the summer, when the sun is more directly overhead, the energy coming from a given column of light will be concentrated on a circle of a certain area. And then this is actually why we have winter, because the sun is lower in the sky, and that causes the same amount of energy from a given column of light to be spread out over a larger area when it hits the ground, because it is at a larger angle. So a lot of times you'll look at intensity of sunlight when you're worried about getting a sunburn, or if you have solar panels, then you notice the intensity of light gives you a lot greater output on your solar panels. Okay, so this also applies to any kinds of waves. Sound waves, as they spread out more, are going to be less intense. And so we're going to jump over to, grab this, here we are. If we think about waves propagating in 3 dimensions now, this is something we haven't really looked at. We looked at waves on a string, which is 1 dimension really, and then we looked in water, like when we went and looked at the pond. Those are kind of 2-dimensional. But if you imagine like a firecracker going off, and that wave travels in all directions, not just along the surface of a lake or something. So you have these 3-dimensional waves propagating out. Well, if we think about what's going on with the energy in that case, so here's kind of another picture of our 3-dimensional wave propagating out. So what this is saying here, this R1, that's the wave at one moment in time, and then R2 is that same wave a little later in time. Well, conservation of energy says whatever energy was released in that wave, now we're not talking about a bunch of successive waves like that animation was showing, but in a single wave, the energy that it contains here is the same as the energy that it contains here. Well, this sphere here is a lot bigger, so we have the same energy spread out over a larger area. And so we would expect the intensity of that wave to go down, because intensity is divided by the area. And we can mathematically look at that. So here we know that the energy at location 1, meaning at radius 1, that wasn't a very good underline, but anyway, is equal to the energy at location 2. And then this equation that I had on the previous slide, that intensity is the power or energy per time over area. If we rearrange that to solve for energy, we get the energy is equal to intensity times area times time. So if I plug those in for both of my energies, I have the intensity at location 1, area 1, time 1, blah, blah, blah. The times cancel out, because if we're comparing how much power is being delivered here and here, how much energy, we want to do it over equal time intervals. So it only makes sense to say that T1 equals T2, so those guys were able to cancel out. That leaves us with this expression here, intensity times area equals intensity times area. Now, what is the area of a sphere, we're not talking about the volume, but just the surface area, the formula for that is 4 pi r squared. So if we plug that in for both sides where we have different r's, according to the different spheres, the 4 pi stuff cancels out and we're left with this nice expression here. And it's often rearranged to look like this. And what this is telling us is that the intensity is inversely proportional to the square of the distance. That's a bad R there, but you get the idea. This is what we call an inverse square law, and we see a whole lot of these come up in physics. And the idea is if the intensity is, say, 12 here, and let's say R1 equals 1 meter and R2 equals 2. So if I double my distance, my intensity doesn't just get cut in half, but because it's squared, it gets divided by 4. So let's just plug in some numbers here. If I1 is 12, I2 is what we're going to try to find. R2 we said was 2, and that's squared, and R1 is 1 squared. We rearrange this, and we're going to get I2 is equal to 12 over 4, or 3. So earlier we had an intensity of 12, and now it's down to 3 just by doubling our distance. So it drops off really quickly. Kind of visually to show what's going on with that, if we imagine the area distributed over not the entire sphere, but if we just imagine one little section of that sphere, a little square right here, that energy is going to propagate out, and at this second location that is twice as far as the first, that will now be distributed over 4 squares, so the intensity got divided by 4. Now if we go, instead of twice as far but 3 times as far as the original length, that 3 gets squared, and so we divide this by 9 now. It's into 9 squares. And really all these inverse square laws are a result of our 3-dimensional space. If we lived in 4-dimensional space, we would have a bunch of inverse cube laws because things would be spreading out in more dimensions. But we don't really need to worry about that for now. Alright, so as this intensity changes, our next question is, how does that affect what we hear? That's what we call sound level. Now this is somewhat subjective. This is kind of based on human perception here. And you always kind of run into problems when you base things on human perception, right? So the question is, if you move twice as far away, you have a quarter of the intensity, as we just mentioned, but in fact that doesn't mean that it is a quarter as loud. It would actually be not get as quiet as that. You would perceive that the sound got quieter, but not a fourth as quiet. And here's a big, wonderful equation where we try to calculate the perceived sound level or perceived loudness of sounds based on their intensity. Okay, so this beta here, the Greek letter beta, is the symbol we use for sound level. And we plug it into this equation here, 10 times the log, this is log base 10, not the natural log, of the intensity, this is the intensity that we've been talking about, divided by I naught, which is a constant. It's 10 to the negative 12th. And that is what we take as the threshold of hearing. For most people, it's not standard. I'll go into more examples of how to use this. But basically, the idea is that they're not linear. What you hear and the intensity of the sound are not proportional to each other. It's logarithmic. And that actually has some advantages that I'll talk about here on the next slide. Also, the units for sound level, you've probably heard of these. We call them decibels. This is actually named after Alexander Graham Bell. And so it's a tenth of a bell. And we kind of make it, instead of saying decibels, we call it decibels, just because it's easier to say that way, I guess. And we abbreviate dB. All right, so let's look at a little chart here of some common sound levels and intensities. So if you took these intensities and you plugged them into that beta equation, beta equals 10 log intensity over 10 to the negative 12th, because that was a constant, then you would get these sound levels here. And so you see it's a logarithmic scale here, so it's not proportional. Also, this is a huge range of intensities that we're able to perceive, right? So we can hear sounds as weak as a trillionth of a watt per square meter up to a watt per square meter, and we can hear more than that, but it would be painful. So this is kind of normal range of the types of things we might encounter. So that is 12 orders of magnitude. That's a lot larger. So this is the range of loudness. We talked earlier about the range of frequencies, and that was about 20 hertz to 20,000 hertz. I guess I don't want the K. All right. So that is a range of 1,000. This is a range of 1 trillion. But the fact that our ears have that kind of logarithmic response actually allows us to hear this range more effectively. If it had a linear response, sounds would quickly get way too loud. There's no way you could hear 1 trillion different levels of sound, but we can hear 1 trillion different levels of intensity. We just don't perceive it as 1 trillion different levels of sound. You need large changes in intensity to be able to perceive a difference in sound. For instance, to increase a sound level of 3 decibels, which isn't a whole lot, requires just a doubling of the intensity. So if you have one airplane is 140, 2 airplanes doesn't go up to 280 decibels. It goes up to 143 decibels, and I can show you mathematically. That works out no matter what intensity you're doubling. So say you've got a rustle of leaves is 10, well, a rustle of twice as many leaves is just going to be 13. Okay, so there's sound level, and on to some calculations.